So within this video, we're going to consider some of the changes that can take place within the water cycle. Some of those changes are changes that happen over time, whereas other changes are changes and variations that can happen within a small area. So perhaps within one individual drainage basin, some natural or human actions can cause changes to the stores and flows of water within the water cycle. One of the most obvious changes that takes place within the water cycle over time are the seasonal variations that we experience between summer and winter. This table gives you a little bit of a summary of those differences. I'd just like to pick out a few of these just to explore in a little bit more detail. So in the summer months, particularly in sort of mid-latitudes, like around the latitude of the UK, we tend to find that total levels of rainfall are lower in the summer months and they tend to be greater in the winter months. So our rainfall patterns tend to be following that sort of pattern. In other latitudes though, those patterns can be slightly different. So for example, in more tropical latitudes closer to the equator, during those summer months, tropical storms in particular are actually more common. That's because the ocean temperatures are warmer and those storms like cyclones and hurricanes are more likely to form when those ocean temperatures are warmer in late summer. So August, for example, is a prime month for when we are likely to experience those sorts of storms. At higher latitudes, so areas further north or south than the UK's kind of latitude, that's where in the winter we're much more likely to see that precipitation falling as snow rather than rainfall. Vegetation also changes during the seasons. So in the summer months, the vegetation is going to grow rapidly, trees will have their leaves, and that in turn links with this next point here about those rates of interception and transpiration being higher. The opposite is true in the winter. So where vegetation dies back or deciduous trees lose their leaves, that actually in turn triggers lower rates of interception and transpiration because those leaves and that vegetation is absolutely crucial in driving these two processes of interception and transpiration. Without the trees or vegetation, those processes don't happen as quickly. Temperatures are also important. So in the summer months, we're going to have higher temperatures. That might be encouraging more evaporation. The opposite would be true in the winter months, where those temperatures are lower, we have less evaporation. That in turn influences the state of the soil as well. So in the summer months, the drier soils are going to be encouraging infiltration. If we think back to the water balance, this is maybe where we might have examples of soil moisture utilisation or possibly even a deficit within the soil. In the winter months, however, we're more likely to see that soil become saturated, so maybe soil moisture recharge is occurring, or possibly when that soil does become saturated, a surplus is more likely. This is true certainly until we get to maybe the extremes of the summer, or if an area experiences a drought, then those soils become almost impermeable as a result of being baked hard by the intense heat and the sunlight. So that might actually encourage more runoff. Conversely, in the winter, maybe some of that water might be locked up for longer periods as snow, or glaciers and ice caps will grow as well. That's another thing that we could consider as happening in the winter months. So that cryosphere is going to expand as a result of those lower temperatures. All of these sorts of factors are also going to have influences on river discharge, and generally speaking in the summer that discharge tends to be lower and it tends to be higher in the winter. So already we can see, just by thinking about seasonal changes, that there are several things that can influence the water cycle over time. Naturally as well, extreme weather events can also cause changes to the stores and flows of water within the water cycle. So at one end of that extreme weather continuum, we've got things like tropical storms, or even just storms that we might experience in the UK. They're going to have some profound impacts on the water cycle. Most obvious of which is going to be related to an increase in the river discharge. So as a result of all the heavy rainfall that comes along with a storm, the discharge of a river, or any river, is going to increase significantly. Storms also tend to bring strong wind with them, and the wind can actually damage vegetation, can certainly blow trees over, particularly when we think about tropical storms. That can have significant impacts on the vegetation. That in turn then starts to have impacts on transpiration and interception that we mentioned earlier. So those processes can be affected as a result of the loss of that vegetation. The saturated soil as well that comes maybe with that heavy rainfall can actually flow down slope and actually becomes eroded from the landscape as it's maybe washed downhill, either through surface runoff or maybe through mass movement in the form of landslides. So that in turn is going to decrease the capacity of that soil to store water in the future. Droughts, on the other hand, have almost opposite effects to this. So we are likely to see significant decreases in river discharge. And as well as that, we're likely to also see a decrease in the surface storage. Things like lakes, rivers, reservoirs are all going to be drying up as a result of that lack of rainfall. We can see in the photo here actually how the soil dries out. We've already talked about how that makes it impermeable. We can get a sense also perhaps that the vegetation in an area is going to die out or certainly become dormant. That then potentially has knock-on effects for the possibility of wildfires. They can become more common as a result of the drought. And the other thing that tends to happen as well, which humans are responsible for, is that we then perhaps switch our sources of water away from using some of those surface stores towards the abstraction of groundwater, so the pumping of groundwater out of the ground. We're going to look at a little bit more at that later, but that certainly has impacts on the water table, causing it to drop as water's pumped out of the aquifers underground. So we can see that extreme weather has an influence on the stores and flows of water within the water cycle. This map here gives you a little bit of an indication of maybe how some of those natural changes can trigger feedback loops. We've talked about feedbacks before, but these are examples perhaps in a little bit more let's start all this again. This map here gives you a little bit more of an indication about how some of these natural events can actually trigger examples of what we call feedback. So what we can see here on this map of California from 2011 through to 2015 and the different levels of drought that are occurring from abnormally dry right the way through to extreme or exceptional drought. We can see over time that in 2011 only a small area of California was subject to abnormal conditions. By the time we get through to 2014, 2015, the whole of California is suffering a drought, and in some cases, or most cases, that is either extreme or exceptional. So this problem is getting worse over time, and this is an example of what we call positive feedback. So over time, that drought is getting worse and worse and worse, and that is because the initial drought is causing other things to happen, which in turn make that drought worse. A couple of examples for you here. So we can think about perhaps initially the drought might cause the vegetation to dry out. That might mean that wildfires or forest fires become more frequent. As a result of those fires, the vegetation is going to die. It's not going to be able to survive that, and therefore maybe there is going to be less evapotranspiration and less precipitation as a result of that. We can easily see then how if there's less rainfall, that drought is going to be made worse again, perhaps triggering this same loop to continue, and over time things to get worse. Same principle in this cycle down the bottom here. The drought might cause vegetation to die. That vegetation is not returning water to the atmosphere through evapotranspiration, and that could result in less precipitation as well. There are other feedbacks that relate to drought, but those are two good examples there of how once it starts, this natural process can be intensified that little bit further. Moving on to think about human activity then, and how human actions can influence the water cycle on a local scale and over time as well. Deforestation is a really important process. In the example we've got on the screen here, we've got two situations. We've got an area, situation A here, which is basically before an area has been deforested, and then situation B here, which is after an area has been deforested. The arrows on here represent different flows. So P represents precipitation, E represents evapotranspiration, and TF here represents through flow. So we can see under what let's say we'll call kind of normal conditions, there's a significant amount of rain falling, but most of that rain is being intercepted and then returned back to the atmosphere through evapotranspiration. So only a small amount is making its way through the soil as a result of through flow into the river, meaning that overall the river discharge is quite low. If we fast forward and think about if we removed those trees, same amount of precipitation going in, but we've got less evapotranspiration coming out because those trees aren't there to return some of that water to the atmosphere through transpiration. We've also got another flow here. We've got overland flow, or sometimes more commonly you might come across that term as surface runoff. So as a result of there being no interception, we've got more surface runoff or overland flow, and actually probably a little bit more through flow as well, and that is going to make the discharge of the river higher. So in the short term, as a result of deforestation, less interception, more runoff, higher river discharge, that could actually lead to flooding in the local area, couldn't it? However, we need to understand that in the longer term, this might actually cause another set of changes to happen. So this time, what we've got in A here, this is the same situation as we had in B over here. So we'll call this what happens in the short term. Okay, so in the short term, just as I've explained, lots of rainfall going in, not much evapotranspiration coming out, lots of runoff, we've got a high river discharge. However, in the long term, that can cause a different change to take place. So in this case, because that water that's in the river ultimately flows out to sea and gets lost from the system, without those trees present, there is going to be less evapotranspiration. If there's less evapotranspiration, there's less water going into the atmosphere. In turn, there's going to be less precipitation. So even though these two flows might reduce, overland flow and through flow, it actually results in there being less river discharge in the long term. And that's because the rainfall that was created originally by all of these trees here in our first diagram, because they're not there, they're not returning water to the atmosphere, therefore there's less water locally within the atmosphere and we're going to get less rainfall. And we see this happen when there's quite extensive deforestation, particularly in places like the Amazon. There's actually sometimes 20 to 30% less rainfall in areas after they've been deforested. So deforestation has a number of impacts, and we often associate it with having kind of impacts like this one in situation B here, where just deforestation leads to higher runoff and flooding, but actually in the longer term other things happen, and over time that river discharge actually gets lower because there are fewer trees to return that water to the atmosphere. Urbanisation is another really important way in which human activity influences the water cycle. On the left hand side here we've got some examples of maybe what might be happening in a rural area. So that vegetation is going to be breaking up the momentum of the rain, it's going to be intercepting the water as it falls as rainfall. It's going to be helping to maybe anchor the soil together, minimising the soil erosion. The vegetation is going to be building organic matter in the soil, which is going to help it to absorb more water. And ultimately, we're going to get less water getting to the river, and it's going to get there more slowly. In an urban area, on the other hand, we have the opposite of those processes happening. So impermeable surfaces, like pavements, rooftops, they're going to cause lots and lots of runoff very quickly. Drainage systems within cities are going to channel that water a little bit like a mini river into the main river channel. So that's going to help direct water from the surface into rivers very quickly. Even the streets themselves acting as small streams or channels to again funnel that water downhill and downslope towards the river. So basically we get this situation where urbanisation results in there being more water getting to the river, and that river water gets there more quickly. So that's a good kind of mantra, if you like, to remember about urbanisation: more water more quickly. Agricultural practices as well can have a number of impacts on the water cycle, and probably something that is often gets quite overlooked when we think about the impact of human activity on the water cycle. First and foremost is how human actions through grazing of cattle on the land or through the driving of machinery across the land leads to soil compaction. So in both of these cases here, the weight of the machinery or the weight of the cows is going to be pressing down on the soil, and it's going to be compacting it. As a result of that, we are going to have less infiltration of water. Soils can't infiltrate as much water if they're compacted by these heavy machines or these heavy animals. And we can see an example in this photo here of just how much more runoff there is down these fields after some heavy rainfall as a result of that rain falling on that compacted soil. So we get more runoff as a result of that soil compaction. Farmers also like to drain their farmland. It's not very useful for farmers to have their fields and their farmland waterlogged. In the past, this used to maybe take the form of drainage ditches being dug into farmland like this. And these drainage ditches act just like little tributaries, funneling the water downslope down to the river much more quickly. Things have moved on a little bit now, and sometimes farmers will install plastic pipes, or what we call soil drains, into the soil, and basically these are speeding up the process of through flow. So they are helping to channel the water through the soil more quickly, getting it downhill, getting it out of the field, funneling it into rivers, which is obviously going to make their discharge increase. Farm machinery, as well as compacting the soil, can also have an impact through ploughing as well. So what happens when a field gets ploughed is those little furrows that are left by the plough, they actually act like little streams themselves. So they can again channel water downhill, causing it to run off the surface much more quickly, especially if those fields are ploughed up and down the hill. So if we imagine a tractor driving down the hill and up and down it like this, creating nice little sort of gullies for that water to run down, that water is going to travel downhill much more quickly. We've mentioned deforestation already, but it's important to remember that a lot of the deforestation that happens around the world is for agriculture. It's in the region of about 80% of the deforestation in the Amazon is for agriculture. And even though crops might be planted in replace of these trees, they do not intercept as much water, and they do not return as much water to the atmosphere through evapotranspiration. So deforestation is significant, and we've already talked a little bit about the impact of that. Irrigation is important as well. So very often surface water can be diverted from rivers and streams and lakes to farmland, and that obviously has an impact in reducing the amount of water stored at the surface. The final problem created by agriculture, which we're going to have a little look at in a little bit more detail in a moment, is, as I've already said earlier, the abstraction of groundwater. So where water is pumped out of the ground to irrigate crops, that can have significant influences on the water cycle. I'm going to have a little look at that in a little bit more detail now. Groundwater abstraction is important because we are taking the water from very, very deep down within the groundwater. Don't worry too much about some of the things written here on this key. We don't need to worry too much about that, but this diagram just shows you quite nicely how, as you travel deeper into that groundwater, the longer it takes for that movement of water to happen. So if we were to go right down into this deeper part of this aquifer here, if we were to drill down, that water is going to have been making its way through those layers of rock over centuries and centuries. That means that when we take that water out, we need to make sure that we do it at such a rate as it's balanced by the amount of water going back into that aquifer through precipitation. It's a bit like your bank account, where if you take more money out of your bank account than you put into it, your bank account is going to get smaller and smaller and smaller, and soon you're going to run into some problems. And the same principle can be applied to those groundwater stores. Now, in sort of mid-latitude regions of the world around, let's say, Europe, this isn't too much of a problem, because actually we get quite a lot of rainfall, and those aquifers are actually being recharged through rainfall. Over time, that rain percolates down through the soil and the rocks and recharges those aquifers. We do still need to be careful that we're not over extracting it, though. The bigger problem occurs in what we might call semi-arid regions, or certainly in areas where we have what we would call fossil aquifers. Okay, aquifers that were filled up centuries or millennia even ago, that are not really being replaced or replenished at anything like the speed at which that water is being consumed. So good examples of that are the Nubian aquifer, which sits underneath the Sahara Desert, or the Ogallala aquifer, which sits underneath sort of the western USA. Those aquifers are not receiving enough rainfall to replace the amount of water that is being pumped out of them. If we have a look at this graph on the right hand side, we can see that in some places the amount of groundwater being abstracted is not really changing very much. A slight decrease in Western Europe there, little bit of an increase in South Africa here, but two countries that really stand out: the United States as being quite a significant consumer of groundwater, but India absolutely dominating here in terms of the amount of groundwater being abstracted each year. Now this is causing real problems in India, because as a result of taking that water out of the aquifer, you are stopping that water from either reaching rivers or from being able to be abstracted for human consumption. So many of the wells that people might use to collect water in rural areas, or many of the rivers or streams that might be used to supply people with water, they're not being replenished because there isn't enough groundwater there to replace the water that's being taken out. So what happens as a result of the abstraction of groundwater is that the water table drops. So the level of water beneath our feet actually falls. We could see that actually this level of water would get lower and lower and lower until we didn't have any left. That has impacts on wells drying up. So people have a problem accessing water that they need. Rivers start to dry up as well, because in the summer months, or in the drier season in some of these parts of the world, it's the groundwater that is keeping those rivers flowing, and as we pump that groundwater out, there is less of it available to actually flow into rivers. The other problem that occurs with groundwater is that the more you pump out of an aquifer, the harder it is to actually extract water. The reason why that water comes to the surface quite easily initially is that the water is under quite a lot of pressure, and therefore that water comes to the surface quite easily. It's a bit like if you had a carton of drink and you stuck a straw into that carton of drink. It's quite easy to get the first little sip out of that carton. But as you get down towards the bottom of that carton of drink, you have to suck harder and harder and harder on the straw. And the same principle applies with our groundwater. The more water that you extract from the groundwater, the harder it is to extract the remaining water. So the more water we extract, the harder it becomes to extract any more water. And that creates a problem when we think about trying to supply enough water for people and for agriculture. So in summary then, the water cycle experiences a range of natural changes, perhaps driven by seasonal variations or by extreme weather in the form of storms or droughts. And it experiences human changes as well. So deforestation in the short term will lead to higher river discharge and flooding, but in the longer term actually leads to lower river levels and even possibly the chance of drought. Agriculture impacts the soil stores, it impacts interception, it impacts surface runoff, and it can have an influence on the water table. And groundwater is being unsustainably abstracted, especially from these so-called fossil aquifers, which are not being replenished at the same rate that they are being used. And that in turn causes the water table to drop, and that creates problems in terms of droughts and in terms of a shortage of water for people.